All right, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for successful, I guess, first day of school, and I just pray that you'd guide our steps today, help us to solve an interesting problem and understand it, Lord. In your name I pray. Amen. All right, so the first problem, of course, is to find an interesting problem. I suggest, since we looked at the heat equation last time, I want to look at an introductory example of, let's say, the wave equation. Here, and then when I finish that, maybe we'll still have time to look at like Laplace's equation, just to show you the major examples. Mm-hmm. And then in future lectures, we'll start looking at like the theory of Fourier transforms, and I'll try to find you guys some specific gory, horrible problems to work through. Yay, yes. So this is actually from section 10.6 of a book I didn't buy for you, and didn't make you buy. Section 10.6 of Nagel, Saff, and Snyder. For what it's worth, but that doesn't really matter. It's also in your book, I just don't want to find it. So partial squared u, again, we're going to, partial t squared is equal to alpha squared partial squared u partial x squared. And again, I'm also just putting off physical explanation for why this is a wave equation to a future meeting, okay? That is, of course, an obvious and important question we should answer, or try to anyway. Here, alpha is a constant, and this is going to be for 0 less than x less than L, all right? And let's see here, and we're given, all right, it has fixed endpoints, so like the endpoints are fixed. So these are the string is fixed at the end, so that gives us the equation like u of 0 t equals to 0 and u of lt is equal to 0, and that's for t greater than 0, right? So it's got basically the string is tied at the endpoints, right? And we're also given an initial velocity. All right, so we're given the partial u. We're given an initial position and an initial velocity for the string. So you know how this works, more or less. New markers. Woohoo! Take you back to school sale at Walmart. Should I share these with abstract algebra, or should this just be for you guys?
Both are for us. Yeah, it's
just for you guys. So, initially, the string is in some particular position, right? So, like u of x comma 0 is equal to f of x for 0 less than x less than L. And also, we're given its initial, I don't know how to, here's a kind of silly picture of it, but, I don't know, it's a silly illustration of it, but partial u partial t of x0 is equal to g of x, 0 less than x less than L. So we know the initial position and the initial velocity of the string. And if I wasn't teaching 6 courses at the same time, I might be able to explain to you why the wave equation is what it is. I guess we could if we took a couple minutes to work it out. I just don't feel like it at the moment. Sorry guys, I'm busy. Some other day. But it is just studying the tension on a little segment. Did either of you have physics with me last semester? No, curses. Last semester I worked out in physics even. Like, it's not hard. You just focus in on a little line segment and study the tension force of the string, and you come to this wave equation with a few simplifying assumptions. But it's not hard to derive this in Newtonian physics.
So you're saying physics 1?
Yeah.
Oh, really?
Yeah, I derived it in 231.
Oh.
It can be done. I'll do it in here someday. Okay. But of course, we need more data than we did in the heat equation, because now we're dealing with a second order differential equation, right? So you guys remember, to solve a second order differential equation, you need initial condition and an initial velocity and initial position, right? So now we got the boundary values here, the homogeneous boundary values, right? And now we've got not only an initial position, also an initial velocity. And so we're hoping maybe the same kind of bag of tricks, separation of variables, paired with the Fourier technique is going to allow us to solve this sort of thing. All right. So let's work at it. Okay. So first of all, I'm going to say, let's see here. You guys probably can tell me. What do you think we should do? U of xt equals to what? Well, first of all, I guess I said, yeah, x. I always have a moment of like, wait a minute, time space or space time? What did I do?
Space time.
I did space time. Okay. Yeah, it sounds better, doesn't it? Okay, so space time. So, yeah, I mean, it's kind of funny, right? Like, if you look at special relativity books, there's two kinds of things that happen. Some people are like x4 is equal to ct. Other people are like x0 is equal to ct, you know? And it just depends on. And then there's also the imaginary, the people who put an I with the time, because if you do that, then you get a Euclidean dot product. Because like I times I is squares to minus 1, right? So if you look at the 4-vector x, y, z, it, or cit, and you take the Euclidean dot product of that with itself, it gives you x squared plus y squared plus z squared minus c squared t squared, which is the invariant interval from relativity. So, but that's kind of fallen out of fashion lately, but early on it was a popular thing. Anyway, I digress. All right, so this, what did you guys, I was waiting for you guys to tell me, what should I do there? What do you think? It's been a long day. Remember we did last time? Separate variables, right? We proposed the solution looks something like, or at least as our like basic trial template for the solution, something like x of x, right? Times t of t. In other words, we can write the solution. Now, I mean, if we believe what we did last time has some analogy here, we don't expect this to actually be the solution. We expect this to be an ingredient that we can form the solution from. Because last time, this sort of thing didn't solve it directly. We had to take an infinite series of these things. Remember? This over here. Oh, sorry, I'm pointing off the map. Oh, anyway, I don't have the series. I think I erased it. Oh, man, I erased it. Oh, well. Okay.
What if it's not some like equation that can be like variably separated like that? Like, I mean,
That's an interesting and open question. Where does separation of variables work? Generally. I don't know the answer to that. I know it works for this.
okay.
And
So we don't know if there like is or is not a solution to like an equation that we can't just like.
I don't know right
use
offhand.
separation
I
of
know that
variables.
I've got this book here by Willard Miller Jr. on symmetry and separation of variables.
Okay.
And the better part, it looks to me like, of his career, he has spent attacking just that question. And I'm not sure what the verdict was. But
I mean, because I just remember from ODEs, like, yeah, it was nice when we could separate them, but things got a lot trickier, and obviously, when you can't.
Right.
You gotta try like all these different other methods and like look at
Yeah, I mean,
like, forms of them.
yes, for first order linear ODEs, it's kind of like right in your face when you can't separate it, right? Like it's like, okay, yeah. Here, I mean, I don't know that much about PDEs, but I don't know of an example, for example, of a PDE which you can't solve with separation of variables.
Okay.
Right off the top of my head.
Yeah.
Maybe if I just made myself sit down and try to come up with one, I could come up with one. I don't know. That's a good question that I don't have an answer to at the moment.
Sorry.
That's fine. That's the kind of questions we should ask. So, look, if we plug this guess into this template, that gives us what? It gives us, we're looking for UTT is equal to alpha squared uxx, right? How's that happen? What goes on here? Well, it's x t prime prime equals to alpha squared x prime prime t, right? Divide both sides by the, divide both sides. You get what? You get t prime prime over t equals to, I'm going to put the, I think it's easier for me to put the alpha squared over here, maybe? I mean, the easiest thing for me to do would be alpha squared equal to 1, but I'll resist the urge. I gotta put it somewhere anyway. This is equal to, right, x prime prime over x. So then what?
Oh, sorry.
So same thing we do every night, right? Try to take over the world. It's here. So this is function of t. This is function of x. So constant, right? So this has to be equal to some constant, let's say k. So what do you know? We find ourselves faced with second order constant coefficient ODEs again. In particular, we gotta solve, what do we gotta solve? We gotta solve x prime prime. Oh, I think it's better, I think for reasons that you can kind of see in a second here, I want to make that a minus k, just for the sake of my writing x prime prime plus kx equals to 0, right? And we also face what? T prime prime plus alpha squared k t equal to 0. So that's what comes to us from there, right? Now, so the boundary values, right? The boundary values, we have what? We've got u of 0t equal to 0. We've got u of lt equal to 0. What's that tell me, actually? So this tells me like x of 0, right, times t of t equal to 0, and this tells me x of L times t of t equals to 0. And these are both what? For t greater than 0. So if, nice. If, I should teach everything like this. If, t of t is non-zero, the only way we can achieve these trivialities is what? We need to require what? We need boundary values for x, right? We need what? X of 0 equals to 0, and we need x of L equals to 0. And again, what are we solving? We're solving x prime prime plus k times x equal to 0.
So how do we know? So I know the variable t, the little t, can't be or is greater than 0. But how do we know that that function itself will never reach 0? Or are we just assuming that?
Well, that function can be 0, but if it's 0 for all time, it's just the 0 solution.
Oh, right. Okay, so we're just throwing out the trivial solution for that.
Right. I mean, the point is, it has to be 0 for all t,
Right.
you know?
Okay.
I mean, we need that equation to be 0 for all t, so
Right.
if t of t is 0 for all t, well then that's just the 0 solution, which is
Right.
not what we're after.
Then this just seems like
So
a
we-
problem for regular ODEs now, doesn't it?
We're solution hunting. Yeah, now we're back to one of the 4 propositions. In fact, the first proposition we covered
Just
in our first meeting.
Just a theorem.
Right, so we go back to proposition blah, 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 and we figure out k is equal to what?
Who's got it?
I think it's n squared pi squared over l squared. So that's k at least, yeah.
Right, so therefore, k equals to, what did you just tell me? N squared pi squared over L squared, right?
Yes.
And our x, we'd say x of n of x is equal to, we got some constant, right? Which I'll put in there, Bn, the sine of n pi x over L. Now, so you guys tell me, what's the difference between this and the heat equation we looked at last time? Oh, let me not erase that. Golly. I was about to erase something that was my point. Here, at me. So, alright, so if you look over here, see if I can get both boards at once. All right, cool. So remember, I was starting to erase it, but this was t of t last time, right? Like, it doesn't matter what k is. We just solve this thing. It's like an exponential, bam, right? We didn't have to think about, oh no, what if k is this or that or the other thing? We just solve it, right? That's not the deal anymore. Now for our t solution, we face t prime prime plus alpha squared kt. So, you know, it's a different animal altogether. But we can still solve it, again, with our 4 fundamental propositions about homogeneous boundary conditions. Right? I still haven't looked up those super expensive Legos you guys told me about. Pretty stoked about them though. I don't know if I should look. I mean, I have specifically
Yeah.
looked for expensive Legos before, but I didn't find those.
Oh, the TIE Fighter one is pretty sweet looking in my opinion.
Yeah.
I think it was like $200-300 or something like that.
Oh, that's like
It had its own plaque. And it was big, I think. I think it was
They're
definitely
very-
bigger than the Millennium
They are
Falcon.
very large.
Sounds wonderful. All right. Okay, so we got to solve t prime prime, right? Plus alpha squared. Now k. What is k? K is n squared. Pi squared over L squared. Right? T equal to 0. So, I mean, in other words, the beta, so to speak, is equal to alpha n pi over L, right? I mean, we're basically looking at, you know, t prime prime plus beta squared t equal to 0 with that beta, right? So we know how to solve that. That's sines and cosines, right? So therefore, t n of t is something like, and see, this is where I regret putting a piece of n over here. Like, I'm going to scratch this piece of n. Gone. And I'm just going to put there's got to be, you got to put constants somewhere. You guys work for these for a little bit, you'll start to see you have flexibility where you put the weight. Like, you could either put it in one part of the product solution or the other. Somewhere it's got to be because you're going to add them. Or maybe you don't need, maybe you could just put the constants to be 1 everywhere and then at the end take a linear combination of them. You have some freedom in these matters, how you construct these things. It's like there's not just one way to build a house, you know? There's like a lot of different ways. So, but
I mean, but that's like restricted to these type of problems because we're only dealing with like, at least with these part, they're only linear and homogeneous, right?
Yeah.
Of course, when we get
Yeah, we're just for the moment looking at linear homogeneous PDEs, the standard examples, heat, wave, Laplace equation. We will later look at non-homogeneous case and some slightly uglier things. But yeah, so but this is my house, so I'm gonna build it how I want, which is I'm gonna put a cement here, and I'm gonna put a cosine beta t, right, plus say b sub n sine beta t, right, where beta is that guy. You with me? So far? Hopefully. So, now, this gives us basically, a way to construct a formal solution. So we're like, okay, so what I'm gonna do, I know that if I satisfy the boundary conditions with one of these, the nth solution, if I add them together, I still satisfy the boundary conditions, right? So a nice sort of general solution to the boundary value problem is just this. It's u of xt equal to the sum n equals, golly, I guess 0 to infinity, and then, x sub n times this t sub n, which working it out is going to be a sub n cosine sine cosine beta t sine n pi x over L, right? And then plus the b sub n sine beta t sine n pi x. I'm just foiling the sine n pi x over L to both, Foiling, what on earth is that? Distributing. Are we not men? Let's speak as free men. Alright, there we go. Sorry. Yeah. So that will satisfy the boundary values. Right. Now, what's left is to satisfy the initial conditions, right? The initial shape of the string and the initial velocity of the string. So, you look at what that is, right? Like, first, let's start with the initial position. U of x 0, well, that's given to be f of x. F of x is some function that describes the initial shape, right? U equals f of x. That's the graph of the string to start with. U is the position off the vertical for the string that goes from x equals 0. Sometimes U is y if you look at like a physics text or something, right? It's actually the vertical displacement of the string off the center line vibration. So this, plug in 0 for t, what happens? Well, sine, gone, and what we got is that this is the sum, n equals 0 to infinity of a sub n. Cosine of 0 is 1, sine of n pi x over L. I hope you start to have a sense of deja vu. This is almost the same thing that happened to us with the heat equation, right? So the point is then to figure out what is to choose a sub n's to fit the f of x. What do? I mean, you can use Fourier theory, right? If you want to be a little bit more hands-on, you can just be like, well, I'm going to multiply both sides. Just multiply both sides by like the sine of, say, k pi x over L. I'm going to integrate from 0 to L. I know that then behaves like a Kronecker delta here, and it selects the a sub kth term, and it gives me a formula for a sub k in terms of the integral of f of x weighted by sine of k pi x over L. So, a little bit...
kind of dumb question.
Yeah,
but for the u of xt, like when you rewrite it in like that formula right there, that's like, is that technically the Fourier transform of it, or is it?
No. This is here. I'm just taking a sum. So this is nothing more than like the sum n equals 0 to infinity of the separated solutions, like the xn, tn.
Yeah. Okay. So this is, we're not doing anything with Fourier yet, really.
No, not yet. The Fourier enters right here when I say, how do I connect f of x to these coefficients? In other words, so like here's the way I usually tell 341 or 334 when I teach it, is I say, okay, so in order to figure out what this is, what you do is you just expand this into its Fourier series. So this has a Fourier series that looks something like sum n equals 0 to infinity of, you know, Cn sine of n pi x over L. And then if these two things are equal, in the same way we can equate coefficients of polynomials, we can equate coefficients of like, you know, like argumented signs, and so it follows that Cn is equal to An. And then there you have half, you figured out what half of the story is for the solution of the wave equation. You figured out the A sub n's.
Okay.
Now, the question of course is how do you actually find the C sub n? Like what's the formula for C sub n? Alright? So, basically the story is this. Let me just go back to here and show you the argument. And we can build this up more theoretically some other day, okay? But I'm just showing you just a straight calculational approach at the moment. Devoid of, you know, a lot of mathematical prowess or anything, just straight computation, alright? So, I'm imagining myself an engineering professor. Just calculate, alright? Strip all the math jargon out of it. Just straight calculation. Let's see here. So multiply both sides, step 1, by the sine of k pi x over L. And I'm using the fact that you can distribute, you know, if you have an infinite series and you multiply it by something, it's multiplying term by term, right? So this is a sub n sine n pi x over L, sine of k pi x over L. Quick reminder, if we have the sine of theta times the sine of gamma, that's minus 1 over 4 e to the I theta minus e to the minus I theta e to the I gamma minus e to the minus I gamma, which is what, minus 1/4 e to the I theta plus gamma plus e to the minus I times theta plus gamma minus 1/4 e to the I theta minus gamma. Let's think about this here. That should be a plus. Plus e to the minus I theta minus gamma. Otherwise known as 1/2 cosine of theta minus gamma minus the cosine of theta plus gamma. Being distrustful with calculations I'm doing at this time of the day, I will check the identity I just derived from imaginary exponentials with something I know about sine. How about like pi over 4? Sine of pi over 4 is what?
Square root 2 over 2.
Root 2 over 2. And so if I put theta and gamma both equal to pi over 4, I should get what? Root 2 over 2, root 2 over 2. It's one, that should be a half, right? Okay. How about if I put down there, pi over 4, pi over 4. So I get cosine of 0 from the first one, and I get cosine pi over 2 from the other one, which gives me 1/2, 1 minus 0. 1/2 equals 1/2. I could have got lucky in my check,
Yeah.
but it's probably okay. Now my point then is that I can take this, right, and I can rewrite this as actually what? A sub n over 2, right? cosine pi times n plus k x over L minus the cosine, did I do right? Oh, sorry, I'm an idiot. What is it? Cosine of n minus k? You're like, how do you know which one's n, and which one's k? It doesn't matter, cosine's even. Right? The point is the subtraction, the difference term has the plus. The addition one has the minus. That's not up for grabs. So over here we get pi times n plus k times x over L. Now, putting the cart before the horse a little bit here. The reason I did that, if it's okay, I'm going to erase the, oh yeah, I better check. I better check on my, my Zoomy. Go down a little bit here and zoom in a bit. All right, it's cool. I'm going to erase this.
Oh, yeah.
You guys have had stuff with me before. I've showed you the imaginary exponential thing before. No? Yes? No? Yes? No?
I know of it.
I've
but
seen
it's-
it, yeah.
Yeah.
I don't know if you showed it to me, but
No. Oh, no. This matters to you guys. This is a tool that you can use. So, sine theta is 1/2 e to the I theta minus e to the minus I theta. Cosine theta is 1/2 e to the I theta plus e to the minus I theta. These both come from Euler's identity, which is this, e to the I theta is cosine theta plus I sine theta.
Yeah. So I was thinking it kind of came from was a rehash of.
Now, you'll see this appear again in complex as you take it. But I tell you what, since you guys haven't seen me do much with this before, I'll try to take some other day and do a little bit more on this then, as we have time. Okay. But that's what I just used. Is like that allows me to derive trigonometric identities. What I do is I just take sine and shift to imaginary exponentials, do ordinary algebra, because imaginary exponentials obey ordinary laws of algebra, and then I convert back. See, this is a 1/2 times 1/2, so that's a sum, so it's a cosine. And so it allows me to derive trigonometric identities that I would otherwise have to memorize.
Is
See,
it-
I don't have this memorized. I actually derive it.
You just do it.
Yeah.
That's useful.
Oh, I see. Never mind. That's not a question for now.
Good. No memorization.
Yeah, I was just wondering about other certain trig identities that we learned where they probably were maybe used with that instead of like other methods.
There is pretty much no trig identity I can't derive using this technique.
That's nice. I like that. I wish I would have learned that.
That I
sooner.
know of anyway.
I should have learned that in like 8th grade.
Yeah.
Yeah.
Well, I mean, like I knew like the basically imaginary part.
You know what?
Electrical.
Yeah.
You absolutely should have learned that in 8th grade. And it is totally objectionable that we as a society have not embraced that. It is very sad that 200 years after Gauss, we still have not accepted imaginary numbers are ordinary and deserve a seat at the table of everyone's math.
Sad.
It is sad, but true. Okay, anyway, so then what you do, right, is you integrate this sucker from 0 to L. So you just say, okay, well, integral from 0 to L of f of x. Keep in mind, f of x is some given but unknown function, right? You integrate this thing from 0 to L, and then there's a little bit of analysis here. I'm assuming that I'm going to integrate both sides of this, right? And so the integral on the other side, I'm assuming we can switch the order of summation and integration. That is a shady, questionable calculation that fails us in general. But it's okay here. So,
Doesn't that have something to do with like the smoothness of functions or?
yeah, it's a question of uniform continuity and the convergence of Fourier series and various other things that I will at some point address, but not today. And again, I'm still at the moment in my happy-go-lucky Math 334. Hey, it's the end of the course. Let me show you a little bit of PDEs mode. Let's see here. I will eventually be more serious and do some things that are perhaps more sobering. Oops, sorry, I think I'm beyond your event horizon.
What are we getting again?
All right, maybe the videos event horizon as well. So, no, I'm still there. Okay, so then here's the thing. What happens when you integrate cosine? Let me not write it out, let's just think through it. Think through these integrals. Integrate cosine, you get what? You get sine, right? Now it's sine times something because it's a. I mean, you get technically you get, for example, you get L divided by pi times n minus k sine of same argument, right? The other one integrates to what? L divided by pi of n plus k, right? Sine of the argument. And then you're evaluating from 0 to L. Sine of 0 is 0. Plug in L, the L's cancel, and you're left with sine of an integer multiple of pi. And if you're sloppy, right, seems like I just said everything is 0. But there's one case that argument I just gave doesn't do anything to you. This is 0 except when n is equal to k. When n is equal to k, this term integrates away as well. N equals to k, this just becomes like cosine of 2 pi kx, which integrates to a sine of 2 pi kx over L, which then is integrated over a full cycle. It integrates to 0. This piece, on the other hand, is cosine of 0, which is 1, and this integrates to L. And so what this is equal to is just equal to a sub k L over 2.
That seems too nice.
I know, doesn't it? So, therefore, what I've just derived for you guys is that the kth coefficient of the Fourier expansion of f of x is simply 2 divided by L, the integral of from 0 to L of f of x weighted by the sine of k pi x over L dx. So there you go, that's a formula for the kth coefficient of the cosine sine term in our solution. Now we're not done, right? That's just half of it. What's left?
The other half.
The BNs, right?
Yeah.
What did we not use yet? What data have we not used? Excuse me.
Our boundary conditions. We use that. Yeah, I don't think we've used our boundary conditions yet. Have we?
Well, we used the boundary conditions to set up the form of the
I think the boundary conditions was what made it possible.
The
What
bo-
made it-
yeah,
didn't
like
make
that.
it possible for the
boundary conditions, the boundary values. Those are what
Oh, that's what you put
that's
in
what that
right
brought us
there.
to the
Right.
general product solution. What we haven't used yet is the initial condition. So let me do that. So so I guess I need to. It's kind of complicated. Over here, we take this thing here, right? And we have to differentiate that with respect to time. Right? Then we're going to plug in time 0. When you differentiate this with respect to time, partial differentiate it, rather, of course, that becomes a sine. Plug in 0, that goes away. When you partial differentiate with respect to time, this becomes a cosine. Plug in 0, becomes 1.
Yeah.
So it's pretty awesome. Partial u, partial t at x0, and I don't want to write it all out, but it's fairly obvious what I'm doing is legit. I mean, if you just go through the calculation here a little bit. We have sum n equals 0. You guys tell me, actually, what should I write here? The camera can't see it, but you guys can. So again, the cosine, the a sub n, sine n pi x, so that's gone because that sets when we plug in 0. So partial differentiate this with respect to t. We get the sine beta t is beta cosine beta t, right? Right?
Can we use the, do we want to plug that beta in from the top in there to help?
That won't help us.
Just
Leave it beta for the moment. Eventually, yes. Yeah. But so plug in time 0, right? Then when you plug in t equal to 0, you're just left with cosine of 0 is 1. So that brings us to the following. All right, so this will be b sub n, which we don't know yet, right? Those are the adjustable, that's the moving piece, that's what allows us to fit the condition, right? It's analogous to C1 and C2 in second order problems in the ODEs, where we can use C1 and C2 to fit the initial position and initial velocity, right? Well, now we have infinitely many coefficients because we're not fitting an initial velocity, initial position, we're fitting a whole sequence of initial velocities and a whole sequence of initial positions because we've got this continuum of the string that we're trying to match. So b sub n beta, the cosine of 0 is 1, so that's just okay. And then we still got the sine of n pi x over L. Yeah. Now that's equal to what? That's equal to g of x. Does that make sense? Now, I want to point something out to you at this point, right? So if you believe in this Fourier expansion thing I've been doing, right? If you believe, then what you want to do then, right, is you want to take the g of x and you want to re-express it in terms of its Fourier expansion. You want to find its Fourier decomposition, basically. That's what it's called. And so to do that, I keep losing my markers. I also have this problem. It's just me. So basically here, this is equal to, right? This is going to be equal to the sum, let's say, c sub n, the sine of n pi x over L, right? N equals 0 to infinity, where what? Where Cn is equal to, by the same derivation I just did on the other board, 2 over L, the integral from 0 to L, g of x times the sine of n pi x over L dx. So I can take the given g of x, which is, I'm being a little bit fuzzy here. I've been trying to work this out for like generic g of x and f of x and g of x to try to show you the idea. So I'm ripping this apart into its Fourier components, and then, so to actually, again, this is what I'm trying to actually find, the b sub n's. So what are the b sub n's equal to?
That over beta.
Exactly, right. So you just, this is something that, this is given, all right? So this is something you can calculate, just annoyingly, but you can. And so with all of that said, that gives us that the b sub n is just equal to c sub n over beta. Where beta is that annoying thing we had over there, which was what? That's actually, yeah, fine. I'll pay the good piper here. C sub n times L divided by alpha n pi. Gosh, mess. All right, so let us collect all of these ingredients together and write the final solution. Don't worry, it's not that kind of final solution. This is liberty. We're not Democrats. We don't. Oh, I'm sorry. Wait a minute. No, I shouldn't say that. Especially not with our current candidate. Let's see here. Oh, wait a minute. No, did I say that? I shouldn't say that.
I'm gonna get some really.
I just shouldn't
YouTube
say
videos.
anything. I tell you, I don't know. All kinds of microaggressions and medium-sized aggressions and
Medium-sized aggression.
all kinds of. I don't know. All right. Let's see here. Pseudo-political nonsense aside, where are we? So u of xt then is equal to, let's see here. Well, I mean, I guess it's not much, I guess I write it again, it's not really going to be that informative, but I'll just do it here. So it's the sum, let me write it again, and just try to emphasize what goes on here. A sub n, I'm going to expand the beta. Cosine of beta was what? Beta was alpha n pi. Oh no. Oh no. That cough is bad. It's a bad cough. Alpha n pi t over L, sine of n pi x over L, plus the b sub n, sine of alpha n pi t over L, the sine of n pi x over L. Right? Where what? B sub n, right, is given like that. And a sub k or a sub n is given like that. In terms of specific integrals of the given initial position and initial velocity. The product of sines, right, and the product of sine and cosine, those can be, well, let me rewrite, let's see here. Well, the a sub n and b sub n don't have to match up, of course. Let's see here. Let me try to think of something real. See if we can write down a solution for, last time we were able to write down specific solutions for kind of cheesy cheesy initial values, right? So let's see, see if we can't quickly think of some boundary conditions, some initial conditions rather, that allow us to kind of circumvent the Fourier analysis. You can circumvent a Fourier analysis when your initial condition functions are already Fourier decomposed. Like you don't have anything to do if it's already a sum of sines. So, first thing to come to mind for me is, how about for this one, we could say like u of x0 equals to, I don't know. First of all, let's put an end to our suffering. L is equal to 1. We found that to be convenient for this kind of discussion last time, right? L equals to 1. And I'll leave alpha alone for now. Fine. L equals to 1. So what could you do? How about sine of, I guess the simplest thing to come to mind for me is sine of pi x, That means that the string looks like this at time 0. And then initial velocity, what do you want to make that? We could do like cosine. I'm not sure that's possible, just guessing. You know, I mentioned last time that you have to be careful, you can propose impossible conditions for your PDE. Assuming that we'll find out soon if that's possible or not. Alright, so, look at that. What is then, for this, just, you know, because we have a minute or two left here, maybe less. I think we're negative minutes at the moment. So this, if you look at, I'm basically saying sine of pi x is equal to this sum. So what is that saying? It's saying the a sub n's are all 0, except for a sub 1, which is just 1. Right, so this basically tells me a sub 1 equals to 1, a sub n is equal to 0 for n greater than or equal to 1. I can't do math. Greater than 1. Now, this one, partial u, partial t, equal to the cosine, is impossible, isn't it? What did I just get done doing? I just got done showing you that partial u, partial t is going to be these kind of guys, right? So, no can do still. Let's make it a sine for kicks 3 pi x. There, that should be possible. Alright.
He used a number.
What? What is this symbol?
I used a number.
It's a funny looking variable.
Hey,
Go backwards epsilon or something.
stop that. Pi is a number.
Well,
Pi is a number.
it's
It's Greek.
some sort of natural constant.
Hey.
Yeah, but
I mean, x is a number. Okay, fine, I know what you mean. Okay, so that means that here, right? What does that say? That says C3 is equal to 1, and Cn is equal to Kronecker delta n comma 3, basically, right? It's 1 if n is equal to 3, it's 0 otherwise. Now what does that say? Remember, we gotta go, but b sub n, right, is equal to Cn over beta, which is equal to what? Kronecker delta n3 over beta. So basically we get b1 is equal to what was beta? So b1 is I think it's L. I mean, so it'd be L over 3 alpha pi, I believe, but that would be 1 over 3 alpha pi in our current choice of variables, right? We said L equal to 1 for the sake of convenience. Oops. Okay, so long story short, what do we got? What's our actual solution then for this rather contrived set of initial conditions? We have u of xt equal to, this infinite series isn't so infinite, right? We just have what? We only have what? Did I say b sub 1? I should really say b sub 3, right? Yeah, thank you. So a sub 1 gives me what? We got cosine of alpha pi t times the sine of pi x, and then plus what? Plus 1 over 3 alpha pi, right? That was our b sub 3. And then the sine of 3 alpha pi t, the sine of 3 pi x. And that is in fact a solution to the wave equation which satisfies those initial conditions. You can easily check that when you plug in time 0, you get back u of x0 is sine pi x, and if you partial differentiate this thing, what happens? The 3 alpha pi pulls out, and it cancels, and you're just left with like a cosine of 3 pi alpha t times the sine. When you plug in 0, you're just left with sine of 3 pi x again. It's easy to verify this in fact works. But we can do so much more because we can pluck the string any which way we want, you know, in compliance with those boundary values. And as long as we're satisfying the boundary values, fixed endpoint conditions, solve this thing. It's just a matter of doing these pesky little integrals. And these integrals aren't too bad, by the way. I mean, they're hard. They can they can be pretty involved because they've got like an arbitrary n floating around and stuff. But you can do it even if you do like sawtooth stuff and you can do some pretty nasty things. Anyway, that's the wave equation. I guess we won't get to the Laplace equation today. Sorry. I think it's important to see these examples. I mean, I could just dive into the Fourier theory, but I think it's maybe better motivation to see how it's used before I start. But anyway, I have to show you what I know at the moment. I don't have time to prepare. Sorry.
Well, it's nice. It's nice to see though. Like,
Yeah,
it's cool.
Yeah,
it's very useful.
Yeah.
yeah, I just,
I mean, those electrical engineers must really love using it. I wouldn't know. I'm not.
I got students to work through this stuff, and what do you say about electrical engineers?
Nothing. I said they must love it. But I mean,
No, I think engineers should know these things. I mean, I think electrical engineers, by and large, are aware of this math. I think it's not hidden mathematics. It's pretty standard stuff. And then, anyway, a good chunk of the semester, though, we will basically be exploring advanced techniques which give you further methods to sort of rip these standard examples apart. And to some limited extent, you can solve things that are more out there. But so much of what we're interested in falls into these basic categories, so I'll stop here.